Today, we're discussing a binary tree from a post order. So this problem is exactly as a previous problem. The only difference is that we have a post order sequence. And today, we're going to be doing this problem by two ways. The first way is we're going to be looking at this by hand. So we're doing this problem by hand. And then two, we're going to be doing this problem via code. Before we actually get started, I want to discuss some truths. So the very first truth that we know for sure is that because this is a post order, that means that this information is encoded as follows. We're going to have the left node and its children. And by the way, when I write AC, I mean and its children. And then we'll have the right node and its children. And then we'll have the node of interest. So that means that this is in that format. So you have to keep that in mind. The next thing that we know is that because we have this particular format where you have left and children, right and children, and the node, that means that the very last element in your sequence, which is this is going to be your root element. So last element is root. All right, so this actually has ramifications. Because you have your last element as a root, when it comes to iterating through this, it's actually more convenient to iterate right to left instead of left to right. The reason why is because typically when we envision trees, we typically draw the tree from the root down to its children. So you could do it left to right. You could do it, it would work. However, if we do it from right to left, one of the benefits is that we can use some of the code that we've already written for pre-order and then just change it a little bit, and then we can apply that to post-order. All right, so let's look at how to draw this by hand using this order sequence here. So we have this as our root element, and again, I'm iterating from right to left because it's just more convenient for us. So 6 is going to be the root element. Put it up here, and then the next element is going to be the element that is to the right of the 6, and that's going to be your 5. And then to the right of the 5, we have a 4. And then to the right of the 4, we have a tilde, which means there's nothing there. And then also we have another tilde. Keep in mind that here in this situation, when we have a tilde, that means we have nothing. That means we have no node. So tilde represents the absence of a node. So because we have tilde for the right and for the left, that means that this is going to be the leaf of this particular path here. And after that, we then have to go back up to the previous node and then define the left. So when we go to the previous node, that brings us back to the 5. And then we're going to define the left of the 5. So the next element that we have is another tilde. So that means that the left of the 5 is going to be a tilde, and there's nothing here. So I can actually erase this because there's nothing there. Now we will go back up to the previous element, and then that brings us to the 6. We must define the left of the 6. So here, this 3 is going to represent the left of the 6. You write the 3. And then to the right of the 3, we have a 5. And then to the right of the 5, we have a 4. All right, now, do you realize here that we have tilde and tilde, which represents that the 4 is going to be a leaf. So therefore, this path here, that's going to be the concluding path. That's it. Next, you go back to the 5, which is your previous node. As you see, the 5 does not have a left defined. And then you must define the very next node for the left child of 5. So we were here last. We then go to the 7, and that is going to be the left of the 5. Now, as you see, we have the same thing that's happened again. We have tilde, tilde, which tells us that this is going to be the leaf of that particular path. So here, that's another path. And We will then go back to the previous element. We go back to the 5. As you see, the 5 has a left defined already. We go to the 3, and then the 3 is going to be assigned a left child. So we are here now. And we have a 2. So with the 2, keep in mind that we have the same situation happening here. We have a tilde and tilde, which indicates to us that the 2 is going to be the leaf of that particular path here. So now that we have fully defined the tree. And this is what we have for our binary tree. All right, so what we're going to do next is we're going to take the insights that we've gained from looking at this and doing this by hand, and then we're going to modify the code that we have for the preorder to work with the postorder. Let's get to it. This problem can be done in 3 steps. The first step is to define a binary tree node. The second step is to define a binary tree. And then the third step is to create a method for inserting those nodes into that tree. So let's look at the very first method, called the step 1. Define, and one called binary tree BT. So define binary tree node. And for this, I will be using Python, and I'm going to use a class because it's just very convenient for me. Call this class btn. And in our init, we'll take in the pieces of information that we care about. So for each node, we need to take in some data, right? That could be a number, it could be a string. In this particular case, we're looking at a number. And then we need to get a pointer to the left node, and then a pointer to the right node. There you go, that's right. Perfect. And then, once we get this information, we then need to assign this to that newly created object once we have a node being created. So we'll do self.data is equal to whatever we've taken for the actual data. Self.left equal to the left. Self.right equal to whatever we have as the right pointer. And that's essentially it. So the reason why this is important is because, again, we're building the foundations. And look at the binary tree node as the actual building blocks of this tree. So now that we have the binary tree node defined, we're going to look at how to define the actual binary tree itself. The next step is to define the binary tree. Step 2. Define, we'll call binary tree BT for short. All right, so similar to the previous step, we'll use a class and we'll do BT. And in our init, we must take in, this is a self, I know it's kind of hard to see, but that's a self. We're going to take in certain pieces of information. So we need to take in the node list, the actual input which is given to us. And then we'll need the null character as well. So let's call that here null character. And we have that there, perfect. Now that we have this, we have to define the attributes of this object based on the input that we have here. So we'll do self dot, and what I'm going to do is I'm going to call node list just NL for short. So we'll do self.nl is equal to whatever we take in as the node list. And do keep in mind this node list is the post order that we're taking in as the input. And then we'll do self.nc for the null character. It's equal to whatever we have for the input as well. One thing that I forgot to add and forgot to mention is that we do want to be looking at the reverse of the node list. Do keep in mind that we're working with the post order. And because of that, it is advantageous for us to iterate through this backwards. So there are 2 different ways you can do this. One, you can take the input, which is the node list, and then you can reverse it. Or 2, what you could do is you can iterate through this backwards. Now, because I want to piggyback off the code that we wrote for the pre-order, what we're going to do is we're going to take the input for the node list, and then we're going to look at the reverse of that. So again, this is very Pythonic. If you're using another language, you would reverse in another approach. But this essentially takes whatever we have for the input and reverses this so that the very first element would be our root element. Next, we need to have the build index defined. So the build index is important because this is going to help us keep track of the current element of interest. So as we're iterating through this node list, we can keep track where we are by looking at whatever we have for this index. And then lastly, we need to create this method, which will be used to iterate through this input and then create the tree. So we're going to call this method, and we can call it self.insert next node. And that's simply it. So here we have the ingredients of the tree. Again, we just have 4 simple attributes. We have the node list. Yes, we are reversing the node list. We have the null character. We define this as tilde because that's what we have in our given input. We have the build index. We are defining that as 0. And then we have the method. This is the engine. This is what causes things to happen, which is going to take our input and then iterate through and create our binary tree. The next step is to define a method for building the tree. So method that builds tree. And this would be a method of the binary tree itself. So we will call this method insert next node. The first part is to define the node. We're going to initialize this node as none, just in case the node does not exist. And then we're going to extract data from the node list. So do keep in mind that our node list is the input, and we'll do self.nl for the node list, and we are extracting data at the build index. Next, we're going to look to see if this data is equal to the null character or not. If it's not equal to the null character, so if data is not equal to null character, it's not equal to self.nc, we will then redefine the node that we declared here. We're going to redefine this node as a new binary tree node using the data that we extracted, right? And then if this node exists, so if we do have a node, we're going to define the right of the node, and to do this we'll call the same method that we are defining here. So we have recursion occurring. So we'll do node.write is equal to self.insert next node. And then we'll do node.left is equal to self.insert next node. Now, one of the questions that you may have is why are we defining the right before the left? So if you recall, we are working with Postorder, and initially with Postorder you have your input as this format. You have your left, you have your right, and then you have your node itself. Now do keep in mind that in step 2, to make it convenient for us, because we wanted to look at this backwards, we reversed our input. And when we do, we'll have the node, we'll have the right, and then we'll have the left. So when we're looking at this from left to right, we will encounter the node first, which is what we are pulling out here for the information. And then we'll encounter the right, and then we encounter the left. And that's why we do it in this fashion. So it's really important that you see that, because it may not be obvious at first glance. Now, once we have the node, we want to return it. So we're going to do return node. And we are returning this node even if the node is none. We still have to return that information. And that's it. So once you have these steps, you can take the node list and you can actually extract the information and build your tree. So again, step 1 was to define the binary tree node, which is what we're using here. And then step 2 is to define the tree. And then step 3 is to actually use a method, which we're describing here, to extract the data from the tree. And that's it.